In this video, we'll be learning how to draw the graphs of polynomial functions. Let's jump straight into some examples. In example A, we want to sketch the graph of the polynomial function defined by f of x equals x plus 1 times x minus 2 squared. To help us draw the graphs of these functions, we'll be following three steps. Our first step is to determine the end behavior of this polynomial function. Remember that the end behavior for a polynomial function is determined by its leading term. So let's try to figure out what the leading term is for this function. Remember that when you're multiplying out a factored polynomial, each term of a factor gets multiplied to each term of the other factors. So if we want to determine the leading term, we just need to multiply together the highest power term from each factor. Now, first of all, the polynomial x plus 1 times x minus 2 squared can be rewritten as x plus 1 times 2 factors of x minus 2. By writing it out this way, we can now identify the highest power term in each factor. So, to find the leading term, we would multiply the highest power term in the first factor, which is x, with the highest power term in the second factor, which is x again, and then the highest power term in the third factor is x again. Multiplying all those things together, we get x cubed as our leading term. And what this means is that our function f of x will behave more and more like the x cubed function as we trace our graph to the right and as we trace our graph to the left. So let's start by reminding ourselves, what does the x cubed function look like? Remember that if we have x to an odd power, its graph looks something like this. So if we want to determine the end behavior of f of x, we can just trace the x cubed graph to the right and to the left. So our end behavior is as follows. As x goes to infinity, meaning as we trace our graph to the right, we see that the graph goes up. So we would write that f of x goes to infinity. And as x goes to negative infinity, meaning as we trace our graph to the left, well, tracing our graph to the left, we see that the x cubed function goes down. So we would write that our function will behave the same way, which means it'll go to negative infinity. So we now know the end behavior for our polynomial function. Our second step is to find the x-intercepts or zeros of our function and identify their multiplicities. In general, if you want to find the x-intercepts for your function, you want to set f of x equal to 0 and solve for x. So here, setting f of x equal to 0, we have the equation x plus 1 times x minus 2 squared equals 0. Now, since we have a product of two things and it equals 0, it tells me that either the first factor equals 0 or the second factor equals 0. So this allows us to split this equation up into two parts. We have x plus 1 equals 0 and x minus 2 squared equals 0. On the left, if we subtract 1 from both sides, we get x equals negative 1. On the right, first take the square root of both sides, we get x minus 2 equals 0. Then add 2 to both sides, we get x equals 2. So for our polynomial function f here, our zeros are negative 1 and 2. We could have also determined these zeros just by using the factor theorem. Remember that the factor theorem tells us that if a polynomial function has a factor of x minus some number, then that number is a zero of your function. So we see here in our function that we have a factor of x minus 2. That's why 2 is one of our zeros. And we also have a factor of x plus 1, which we can think of as x minus negative 1. That's why negative 1 is the other zero. As for the multiplicities, you just want to look at the powers of the factors. The x plus 1 factor has a power of 1, even though it's not explicitly written. So we say that negative 1 is a zero of f with multiplicity 1. If we look at the x minus 2 factor, we see that the power there is 2. This tells us that 2 is a zero of f with multiplicity 2. Now that we have the end behavior and we know the zeros and their multiplicities, we're ready to draw a sketch of our function. First, let's draw our x and y axis. Since this is just a sketch, we'll only mark the x-axis. The first thing we'll do is we'll plot the x-intercepts for our function. Remember, the x-intercepts are the same as our zeros, and they are at -1 and at 2. Next, we'll go to the leftmost x-intercept, and we'll ask ourselves, what would the graph look like if we were to continue to the left? There are two choices. The graph can either go up or it can go down, and the choice you make depends on the end behavior for our function. Looking at the end behavior, we have this statement. As x goes to negative infinity, meaning as we trace our graph to the left, f of x goes to negative infinity, meaning our graph goes down. That's why when we draw our graph, we'll draw the version that goes down and to the left. So again, starting from the x-intercept, we'll go to the left and go down. Next, we're going to work our way to the right. Our goal is to connect each of our x-intercepts together, but the way we do it depends on the behavior of our function at these x-intercepts. At the x-intercept -1, my function can behave in two ways. The function can either cross the x-axis or it can touch the x-axis and bounce off. The behavior will depend on the multiplicity of that zero. At -1, the multiplicity is 1. And remember from our previous video, we learned that if we have an odd multiplicity, your graph crosses the x-axis. So at -1, we should draw our graph crossing the x-axis here. So we draw something that looks like this. Now what we want to do is connect this segment to our next x-intercept. So take this segment and bring it back down to this x-intercept. When we reach the x-intercept at 2, our graph has one of two behaviors. The graph can either cross the x-axis or it can touch the x-axis and bounce off. We need to decide which of these two options is correct. Again, this will depend on the multiplicity of our zero. At x equals 2, the multiplicity is 2. And remember from our previous video, if we have an even multiplicity, the graph touches the x-axis and then bounces off. So drawing something that touches the x-axis and then bounces off, we would get something that looks like this. One thing to note is that this last segment that we drew here is consistent with our end behavior. Remember, our end behavior tells us that as x goes to infinity, f of x goes to infinity, meaning if I trace my graph to the right, the graph is supposed to go up. And that's what we've drawn here. So this is how we use the end behavior and zeros and multiplicities to help us draw the sketch of a polynomial function. Now let's look at example B. Here we have a function g defined by g of x equals 1/2 times x plus 2 squared times x minus 1 cubed times x minus 3. If we want to draw a sketch of the graph of this function, all we have to do is follow our 3 steps. Our first step is to determine the end behavior. Remember that the end behavior is determined by the leading term. So let's figure out what that is. Again, we can write out the factors of g of x. That way we get a sense of what things would look like if we were to multiply everything out. So g of x can be thought of as 1/2 times x plus 2 times x plus 2, and then 3 copies of x minus 1, and then 1 copy of x minus 3. So to figure out the leading term, we want to multiply the highest power of x that's in each of the factors together. We'll be multiplying together the 1/2 with the x and the x's in each of these factors here. So we'll end up with 1/2, and then there are 6 x's, so we'll have 1/2 x to the 6th power as our leading term. Next, let's think about what 1/2 x to the 6th power looks like. Remember, when we have x to an even power, we know that it has a U shape. So x to the 6th looks something like this. 1/2 x to the 6th. The 1/2 is just a vertical scale, which means I'm going to be compressing our graph by a factor of 1/2. So we have a smushed down version of that. So 1/2 x to the 6th looks something like this in blue. So remember that as we plug in larger and larger positive or negative values of x into our function g behaves more and more like 1/2 x to the 6th. So if we want to know the end behavior for g, we just trace this blue graph to the right and to the left. So here, as we trace to the right, as x goes to infinity, the blue graph here goes up, which means our function g of x is also going to go up, which means that g of x goes to positive infinity. And as x goes to negative infinity, meaning as we trace our graph to the left, well, when we trace this blue graph, the blue graph goes up on this end as well. So our function g of x will behave the same way, which means it'll go up. It'll go to positive infinity. Now that we've determined the end behavior, our next step is to find the x-intercepts or zeros and their multiplicities. This time, we'll just use the factor theorem to tell us what the zeros are. Remember, the factor theorem says that if we have a factor of x minus some number, then that number is one of our zeros. So for g of x, we first have a factor of x plus 2. X plus 2 can be thought of as x minus negative 2. So negative 2 is one of the zeros of our function. Now this factor x plus 2 is squared, so this tells me that the multiplicity is 2. Our next factor is x minus 1, so that tells me that 1 is one of our zeros. The factor x minus 1 is cubed, so this tells me that 1 is a zero of g with multiplicity 3. Lastly, there is just one factor of x minus 3. So this tells me that 3 is a zero of g with multiplicity 1. Once we've identified the zeros and the multiplicities, we're ready to draw our graph. So first, let's draw our x and y axis, but we'll only mark down locations on my x-axis. Next, we want to put down our x-intercepts. We have x-intercepts at negative 2, at x equals 1, and at x equals 3. Let's now go to our leftmost x-intercept. We want to decide if we were to keep going to the left, will the graph go up or will it go down? To decide which direction it'll go, we look at the end behavior. Specifically, we see that as x goes to negative infinity, meaning as we trace our graph to the left, g of x goes to positive infinity. It means our graph goes up. So on our graph, we'll draw something that goes up and to the left. Next, we want to continue our graph to the right and connect each of our x-intercepts. But at each of the x-intercepts, we want to be mindful of the behavior of our function there. Let's start with the x-intercept at negative 2. The two possible behaviors are the graph can cross the x-axis at that x-intercept, or it can touch the x-axis and then bounce off. Its behavior is determined by the multiplicity of that zero. At negative 2, the multiplicity is 2. And when the multiplicity is even, the graph touches the x-axis and then bounces off. So let's draw our function touching the x-axis and then bouncing off. Next, we want to connect this with our next x-intercept. So let's bring this back down to our next x-intercept. At this x-intercept, again, we have two choices. The graph can either cross the x-axis or it can touch the x-axis and bounce off. From step 2, we see that at x equals 1, the multiplicity is 3. And remember, when the multiplicity is odd, the graph crosses the x-axis. So let's draw our function crossing the x-axis. And next, we'll bring this back up towards our next x-intercept. Again, at this x-intercept, the graph might either cross the x-axis or touch the x-axis and bounce off. Looking at our chart in step 2, for x equals 3, the multiplicity is 1, which means it has an odd multiplicity, which tells us that our graph crosses the x-axis. So let's draw our graph doing just that. And we also see that this last segment that we drew is consistent with the end behavior, which says that as we trace our graph to the right, our function is supposed to go up. So in this video, we've gone through a couple of examples of graphing polynomial functions. We'll do some more examples in our next video to give you some extra practice.